you do realise that this is a big sacrifice for me. I come from New South Wales, and tonight is State of Origin night. And I'm a Blue, so that means that I'll be missing the Blues beating Queensland. We missed out on the first night, but anyway, we're going to win tonight.
Tell him he's dreaming.
I'm not dreaming. But it's an important subject, Dross. A pretty mundane kind of subject. Not much can be said about that makes it interesting. However, we are beset by the legislators to make problems for us. And we'll be covering part of that tonight, but I do recommend that you do your own research about where you live, particularly in Victoria. I've learned even new things tonight about the legislation covering Dross. So let's just talk about what it's going to be, our subject tonight. Now, Gary keeps reminding me not to look at the screen. I've got a little picture here of me, which is going to be used as a recording. So I've got to look at this little picture, and hopefully when I see this word, what is Dross, then you'll see that up on the screen. If not, we're going to sack Gary. Now, it's the waste material. Now, just about anybody that melts aluminium is going to create Dross. Now, commercially, there is no way around this. I mean, there are ways to melt aluminium where you won't make Dross, but that's really in the realms of science fiction when it comes to commercial applications. However, let's just talk about what we've got. Now, it's a very, I mean, we all treat it as something that, we've been dealing with for years and years and years. Now, really, it's just a chemical compound, and it's interspersed with the primary metal from which it originates. And the aluminium dross, which forms generally, which is an oxide. That's the principal part of it with molten metal, and reacts with the other oxides within the metal. Now, in die casting, and in gravity die casting, and in sand casting, generally we have it mixed up with silicon, magnesium, and a few other odd bits and pieces. Now, the other components, apart from aluminium oxide, Al2O3, is magnesium, MgO, and also we have it in some alloys. There's some zinc in there, and also there is other materials that really go to do that. Now, it'll be reflective on the type of melting process that you use. If you use a reverberatory furnace, then you're going to end up with some carbonaceous metal in there as well. So dross is a term that is very widespread, and therefore we don't need to. There's a typical examination of the part of dross, and you can see, you would recognise some of those metallics in there and some of the oxides. When we see the word down the bottom, salt fluxes, we have traditionally been taught that you have to reduce the amount of residual metallic aluminium in the dross. And you try and make the dross as dry as you can with respect. So let's talk about the type. We have white dross, which will allow a certain amount of recovery of aluminium to the tune of up to 70%. Black dross, is a high salt content one where you flux the hell out of it, and you might only have 12, 15, 20%. Now, salt cake, which is after smelting. Globally, there's about 3 million tonnes of secondary aluminium dross produced each year. 95% is stockpiled in landfill sites. Now, the authorities have got onto this, and they don't like this. So, because effectively, dross is a hazardous material. And that's the way that EPA judge what dross is. It's a material that cannot be openly dumped into landfill. So there's basically two types that we come across, and that is wet dross, which has a high percentage, and then we talk about dry dross, in which often these salts are being added to it to try and reduce the amount of aluminium in it. There may be a case down the track that we may not be producing dry dross from here on, because it is very difficult to dispose of dry dross. So, now let's talk about the hazards. Aluminium dross is regarded as a hazardous waste because of the presence of moisture it can emit. And when it's wet, it'll produce harmful ammonia gas. And that comes from this little formula here. And ammonia is the NH3 part, and that's the part that the EPA don't like. They don't want this going into landfill, and then it gets wet when the water table rises, and then we end up with ammonia smelling, and that the neighbours don't like that. One tonne of dross is capable of releasing 109 cubic metres of ammonia. So you get some idea of what could be done. Now, maybe down the track there could be a way around this whereby we use the ammonia, but not in the short term. It's not going to happen. Soluble chloride salts in dross can infiltrate soil and groundwater, polluting the environment. In other words, when the dross is in the salt form, it will dissolve with water and will then go into the groundwater around the tip. Excuse me. Now, basically, the waste material responsibility is yours, unfortunately. I had a little expression here. Graham wasn't able to fit this into the slide, but basically it says cradle to grave. You make dross, you have to worry about its life. That is what you are charged, that is your responsibility. So I'm just reiterating that the responsibility of the plant that makes it is kept with them until you dispose of it in a responsible manner. Now that includes, this disposal business has got quite out of hand with the authorities when it comes to storage, transport, processing and disposal. Now if we treat, if you look at the EPA in, excuse me, in Victoria, you won't find the word dross. It's kind of been accumulated under these other materials. And so that makes it even more of a challenge, because we know that we can't melt aluminium unless we make dross, yet they're saying to us, well, you've now got the responsibility of getting rid of it. So the legislation has become quite complex over the years. And so there are federal laws, and that could relate to the export of dross. There are state ones, which means that the dross has to be disposed of in each state under their own legislation. In Victoria, and I'll spend most of my time talking about Victoria, there's even legislation now to transport dross to the only company that I can identify that can process dross, and that's in New South Wales. So you even need a permit to talk about getting the stuff across the border. So there is going to be issues about that. They're not some insurmountable, these challenges, but you have to be aware of them. And those people who are not aware of them, technically, are breaking the law. So, environmental protection authorities, the legislation is administered by the EPAs and the federal government in the states and the territories. Now, it's in the states where most of the direct legislation is. And that's where you've got to look at what you're going to be able to do and how you do it. Now, originally, the companies that can process dross were companies that were mainly involved in the processing of primary dross. And I will get to this. And primary dross meaning for the primary smelter, because they never bothered to worry about the dross that they produced. They just on-sold it to a smelter that specialised in treating dross. In fact, we'll get up to it shortly. Have I missed the slide about
the safety data sheet?
Yeah.
Yeah, that was back.
I did. Can I go back?
Try it.
Pardon?
Maybe try the up arrow to go back.
Yeah, I think it'll go back.
Yeah.
Yeah, okay.
Yeah.
It was right down the bottom of one of the slides.
Yeah.
Doesn't like that. So try it if you want.
I was going to show you a slide. I'm not going to go over every page. All I can tell you, in a primary aluminium smelter, where where all this legislation initially started, in the case of a company in America, and I could only find an American primary company to show you what a material data sheet looked like for Dross. And I was just going to show you that there were 16 pages on a material data sheet for Dross. Now, if you've got 16 pages on every product that you've got, your oils and your hydraulic fluids and whatever, and your turnings and whatever, then you'd know that this was a big event. And that's what it is with the primary people. They judged it as a big event. And effectively, they could see down the track that this was going to be a big problem. So they started to do it all in-house. And so effectively, the first smelter that I knew about that could handle dross internally, a primary smelter, was Point Henry in Victoria. And they proceeded to process their own dross. And that is an Alcoa operation. And that gradually moved over to the other company. Where is the other one in Portland? Yeah, yeah. And so they gradually were able to start processing. But one of the last ones happened to be near where this last processor of dross is in New South Wales, happened to be near the old Alcan plant. And that plant was only maybe 5 or 6 kilometres from where the processing could take place. And they were now on their own because those Alcan people, or if you like, the Curry smelter, as we refer to it generally, has to process their own dross now. And so they don't need the services of that processor over there. But that didn't mean that that particular company would stop, because they had another issue that they needed to produce. They needed aluminium to make what they call pucks, which are used as deoxidant in the steel industry. So they had a big contract for that. So they still need it. So they're happy to process dross. Now, basically, we're going to talk about avoiding, reducing, reusing, recycling, recover and treatment, and the disposal of dross. To avoid it, well, we know. I've already said it's impossible to avoid it in our environment. To reduce it, that's definitely possible. To reuse it, you will get some of it back, or if it's only a small quantity you produce, and when I say small, I'm talking about under 20 tonnes of dross. Right? And those people, they'll only reuse it if they'll buy back the metallic content. To recycle it, well, that's very limited about treating how well you can treat the dross. It's quite difficult to do. You only recover the metallic part of the dross, and you have to use a contractor like the one in New South Wales to do it. And then it's his responsibility then to have it in a form that can go to landfill. Now that company, as I said, was located in the Hunter Valley in New South Wales, and it was an independent company. They didn't have any deals with any primary people, except that they were processing dross for all the primary smelters in Australia, and one of the last ones to handle dross processing was the Tomago smelter in New South Wales. So it's only dry casters, or if you like, gravity and sand casters who accumulate dross. This is your only avenue to get rid of it. Unfortunately, this plant was almost burnt to the ground. Certainly the part of the plant that was processing the dross, the rest of the plant survived. But the part that processed dross just was burnt to the ground. And it's taken them about a year to get the plant up and running again. In fact, it's a bit over a year, I think. And how do they treat it? I mean, it's interesting to realise that when they treat dross, they use a rotary furnace. And when I mean rotary furnace, it's a total rotating furnace. Okay, now, and sitting on top of the aluminium dross is a salts. Now, salts act a bit like alloys. As you know, if you add silicon to primary aluminium's got a melting point of about 800 or 900 degrees, 800 degrees something, isn't it, Gary?
A bit long.
Yeah. And then you've got silicon, which is around about 1200 and something. Yes. And then, but as you add it to it, the melting point comes down, and it comes to a point which is the eutectic, which nominally for aluminium and silicon is about 12.7%. Now that is why we use an alloy called 401. And by the way, if you want to blame anybody for this funny nomenclature system that we use, 401, 313, etc., here he is. I invented that right there. But I did it in conjunction with a Comalco guy called Perce Harrison, his name was. And so I really take the blame for all of that. Now, so effectively you have the dross on the bottom of the furnace, and by this time some part of it's starting to liquefy, and then you've got these salts or combination of salts. Principally it's salt and potash, that's roughly what it is. And it's got a melting point of around about 750 degrees centigrade when you add it to it. And so that happens to be a nice temperature to process the dross, right? And so what happens is these salts, they grab the oxide out of the dross and suspend it into the salt. And so in the end, you have relatively oxide-free aluminium on the bottom. And so what you do then is you divide it off, you get rid of the salt, and then you get rid of the aluminium, and then you can either, if it's tolled, then it goes back to the die caster. If it's not, they would have done some deal of buying it from you. Now, the problem of just even moving it into New South Wales now demands a permit. I might just break here and just ask Angus, would you mind just explaining what the latest is when it comes to transport into New South Wales?
Yeah, so my name's Angus Robinson. So transporting into New South Wales dross now, apart from the chain of responsibility certificates you have to fill out the reportable material, now you need an A12 permit from the EPA in Victoria to move the reportable material from Victoria to New South Wales, apart from the other stuff you have to do, which takes about 42 days to apply for. And then once you've got that permit, then you're allowed to, then you have to add it to the certificate, year, each like you do with the normal reportable certificates you have to send for any other materials. So it's sort of an added step that we introduced in the last year and a half.
Thanks, Angus. Yep. Now, so you can see that this is getting complicated, and that creates real problems. The fact that in most cases, so what I did then, see, I was given a brief through Graham and ADCA to work out what we should do. Unfortunately, I'm not going to give you many conclusions tonight as to what to do. I'll tell you the facts, but I can't give you real conclusions because it's become more complicated as time has gone on. As an example, I took Angus up to Sydney. I live in Wollongong, and Angus obviously in Victoria, and I met him at Sydney Airport, and we went to the processor and had a meeting in his office. A lot of the things we were told at that meeting haven't turned out to be really true, and that really complicated it. And some of the things that were said is there were 3 processors or purchasers of Dross in Victoria, mainly in the scrap field. You know, they were scrappies who would buy the Dross, and those people had the permit to move it and pick it up from your plant. As it turned out, at least all but maybe one has reneged on that issue. In other words, they say, oh, look, we've thought about this and we think it's a bit complicated. So we don't want to get involved in Dross. Right? Now I'm talking about the likes of Sims. Right? I can mention their names because initially I was told that they would be a buyer, right, of Dross. There was another company called Infrabuilt, and they were also told, I was told that they would buy Dross. Okay? There was a third one, I'm just trying to remember now, but anyway.
New South Wales too, wasn't
Yeah, well, there was one in New South Wales as well. As soon as I rang them and mentioned the word Dross, they all ran for cover. Right? They didn't want to even talk to me about it. I spent hours and hours on the phone, firstly trying to track down the most responsible person within those scrap companies to tell me what they could do about the purchase of Dross. And in all cases, they took off for the bush. They didn't want to know, really. And so, and then they got very picky about what kind of Dross. And if you remember when I went back and we spoke about wet Dross and dry Dross, then they'd say, oh, well, we might buy wet Dross, but we certainly won't buy dry Dross. So that does create our own problem. Should we be treating Dross to make it? Because it might be better if we don't. Right? So that creates another problem. So with the issue of transport and the issue of getting certification to even move it across the border, then that is creating other problems. Now, we didn't stir anything. We didn't get the pot going. We were trying to be an independent assessor of this issue. And it was really a bit eye-opening to us. And I might add, Graham has continued some of the work in Victoria and spoken to several people. And I've spoken to die-casters in South Australia and in New South Wales and in Queensland about what they do with it. Most people seem to think that their scrappy will take it. Now, when you look at the legislation, and I didn't bat on any of this, I just thought, well, if they think that the scrappy will take it, then let them go, right? One other company, I was told, was trying to export it. Now, when you look at the legislation, you can't export it unless you've got pretty heavy commitments with the licenses. So that could be a difficult one. Now, when we get up to reducing Dross, that is where we can help because we could do some things. Basically, if we reduce the amount of dross production, then obviously our problem is less. So, and it can be reduced. And training your staff is one issue about throwing clippings, what I call clippings, when you trim a casting and you end up with little fine bits of metal and they sweep them up and throw them back into the melt. I suggest that should finish. You know, it creates more dross than it's worth. Obviously, the furnace conditions are important when you're making dross. So it's important that you have a good furnace. Basically, dross has its own way of protecting the aluminium from any other conditions within a furnace. If you have dross sitting on top of the furnace, and I see many foundries, particularly if they've got crucibles, they're always pushing the dross to one side. And they effectively are creating another barrier for the, not a barrier, another way in which the dross can be produced. So the least you do to the surface, the better it is. So you've got to be careful that you don't agitate the melt to make it worse, right? Because that will make more dross. Now, obviously, one of the best ways to reduce dross is to reduce scrap within the plant, because that's probably where most of your excess dross comes from. We can't do much about melting ingot, even though ingots produce a very small amount of dross, really. The surface area to weight is really on your side. So it would be better if you make castings that were saleable every time. That's a big issue. Now, reducing runners and overflows, and I'm going to ask Graham now to start his part of the bargaining on this particular one, because this is where we feel as though you've got to help yourself to try and reduce the amount of dross within your plant. Thanks, Graham. Don't forget to stand here.
Oh, yes.
And read it here.
Yeah, read it there.
Yeah, so as Eric said, ingots themselves, they've got a very high ratio of the surface area to the volume. So the surface area, of course, is where the aluminium comes in contact with oxygen, and all your ingots have got oxides all over the top of them, and that's going to make your dross. When you put the ingot into the furnace, that dross is going to float to the top, coming off the surface of your ingots. But actually, it's a very low percentage because you've got a lot of volume in there, and the surface area ratio is pretty small. So that's not too bad. The next step is most of the dross that you're actually producing, the excess dross in your plant, comes from remelting runners, overflows, and other offal. So offal is anything you're not going to send to the customer because you've got to do something with it. And then the ratio of the surface area of that, of a casting or a runner or an overflow or a sprue, all that is much higher. So obviously you throw that back in the pot and you're going to make a lot more. I mean, we've observed that in our plant, you know, if we just, some jobs we just run ingots, hardly make any dross. As soon as we start putting the runners and that in, you see it, it's all coming. It's probably makes about 7% and probably maybe 1% on the ingots. So it's a huge difference. Okay, we've got to make runners and you've got to have sprues and you might have to have overflows. But what you need to do is keep them to a minimum. I came across this on the internet. It's a picture of a runner that somebody's got. It's an aluminium part, obviously, a cold chamber part, and they are boasting about how fantastic the runner is, okay? And a lot of people would say, oh yeah, that's fantastic. But if you have a look at it, and you have a look at the size of the runner, and you have a look at the size of the parts, 4 little parts, little parts with a thread on them, and they're tiny. And then you've got great big overflows on them and huge runners, and that, just looking at it, is miles oversized. If I go down there, this die, the runners and the offal is 80% of the mass of the shot. So you're going to take a shot, 80% of it is going to have to remelt, 20% is going to the customer. That's not good, even though that company thinks they're doing a fantastic job. That's because nobody looks at the runner. The guy designing the die, he doesn't think about that. He never gets the bill. The bill goes to the company, they pay it every month. But what's it doing? It's generating a huge amount of dross. Not only is it the dross, is it? It's also the energy. It's also the labour to handle it and do all that. So there's a total disconnect between the person who designs a runner system and the person who pays the bill. They don't even talk to each other. So that's a huge problem in our industry. And I've been to plants all over the world. It's the same everywhere. Nobody thinks about it. No big deal. It seems like nothing. Seems like a lot of effort for nothing. But actually, it is big dollars. Here's a runner here, a runner system, which is what we call optimum runner sizing. So this particular die makes 5 parts, 5 different parts. The required runner size has been very accurately calculated. The runner mass is 15% of the shot, compared to the other one was 80%. So you can see the difference, right? You're going to throw those back. If you have a look at the runners, you have a look at that sprue, you have a look at the size of the runners, people look at that and they say, that'll never work. That'll never work. Well, it works, it makes millions of shots. So the industry's got this thing in its mind, you've got to have big runners, huge runners. They never calculate it. So why do they keep making big runners? Well, because they do what's done in the past. I ask people that, why do you make them so big? Oh, well, that's the way we always do it. So, of course, you've got to copy what was done in the past. The boss is never going to criticise you for making something you've always done in the past, but it's a silly way to do it. You should calculate it, exactly. It's not that difficult to do. You need to have training, you need to be trained how to do it, but you calculate exactly how big the runner needs to be at every point along. Don't make it any bigger. It's not going to do anything. So it's a big deal, really. Now, there's another one here about the rocker cover, and I'm going to actually ask Eric, because Eric has this was one he had personally was involved with.
This was a rocker cover that we made for Ford. In that year, it was a Falcon part. In that year, we made, or they made, 109,000 Falcons. I mean, this is going back a few years, as you can imagine. And the way we designed the rocker cover, we actually had overflows all the way around the casting, all the way. And it added up to quite a weight in aluminium. Also, they needed spare parts, so there was about 10,000 more required. So let's say approximately 120,000 parts a year were made with a rocker cover like that. And then we started to think about these overflows around it. So we got the tool makers to weld up the gate that went to the overflow. And we left some venting in there because that seemed to be important. And we calculated the amount of metal that we stopped going to the scrap. And then we calculated the energy to remelt that scrap. And then we calculated the dross, etc., that we lost. And in this case, in 1 year, we had saved, by welding up all those overflows, $1 million. Now, you might find that a bit surprising, but over 120,000 castings, that's how much we saved by doing that exercise. And I might add, the castings were perfect. So effectively, when we designed the dye, we overcompensated by having all those overflows on the path. We didn't calculate it, in other words. And by cutting them out and having proper venting, it's not a difficult shape to make for a die cast. There is a rocker cover like that. And so you by reducing the amount of eliminating the overflows, we didn't need them, as it turned out. In fact, the more I go around factories around the world now, I see a lot less overflows than I used to see 30 or 40 years ago. So you've really got to think about overflows and venting, because that's where a lot of the dross is.
So we're getting to the end of the night, just a few more to go. So we've got some conclusions here. So I think we all know that dross is a significant issue for all non-ferrous casting plants. We've all got the problem. We cannot eliminate it, but the only thing we can do is reduce it, and that's number 2. But the first thing we should do is exactly try and reduce it. We should change the policies in our companies and say, all right, who's responsible for making all these extra remelts? Why do we do it? Let's start a program and get it down. Treatment of dross, as Eric's pointed out, does require specialised plant and equipment. And this is, it's just the fact of the chemicals that are in there, and if anything, we need to do it properly. Storage, transport, treatment, as Eric said, requires careful planning and management and permits and all the paperwork, as Angus has said. Significant penalties can apply for non-conformance. So I think this is the issue we're all going to be aware of. There are laws there, and just if we go and give a pile of dross to somebody and they take it away, the big danger is if they don't do the right thing, it'll come back to haunt you, and they can prosecute you as the die caster for not, because you're responsible to make sure every bit of it is disposed of according to the laws of the country. So you can't get out of it by giving it to the scrappy. I put this up here. I was thinking about it, and I thought, all right, well, what would be the ideal if we could think about going into the future? How might it be done? What's possible? So this is kind of what you're looking at. You've got your casting plants over there, high pressure plants, low pressure, gravity, sand, investment casting. They all make dross, but it's not just one kind of dross, it's all different drosses of the different alloys. But one way or another, they have to go into some sort of dross processing plant. And if we say, what would it be like in the future? Maybe we can be more advanced. Maybe there are better ways to do it. Maybe there's new technologies that have come along. In looking at the internet, remember that number, 3 million tonnes a year produced annually around the world. There are actually a lot of companies working on this. If you go and have a look on the internet there, you'll find a lot of research has been done mainly by the big aluminium companies, because this is a huge problem worldwide. I mean, in the past, throw it in the landfill, doesn't matter. But most countries now are bringing in these sort of laws. They'll start enforcing them, and you won't be able to do what we've done in the past. So there are a lot of researches going on in terms of totally different ways of doing it. I read one there where some people are working on a process where they don't heat it up at all. They grind it up into very fine particles. They put it into water deliberately. They get the hydrogen gas out. They're trying to work out if it's possible to get the hydrogen out and get money for it and other things. And eventually you have nothing that's going to hurt the environment. So over there we say, all right, neutral gases. So in other words, you want to make sure anything coming out of this process is neutral, can go into the atmosphere, it's not going to cause any problems. Down the bottom, if you've got any solids coming out of this, you've got to make sure that the solids coming out of this process are neutral. They're not going to hurt the environment. It can get water on it, it's not going to matter. It's not going to flow down into the groundwater and cause problems. Because ultimately, if you put it in the landfill, okay, they do have clay-lined pits these days, as we know, tips that have got special requirements so they don't leach into the soil. But of course, it costs a huge amount to have those sort of disposal equipment. Neutral liquids, well, okay, probably H2O is probably the only one that's going to be totally neutral, but ultimately anything that's going to end up in a waterway can't hurt the fish or the bacteria or anything. So, and then maybe some valuable gases can come out of it, like H2O, oxygen, maybe any others, who knows. The metals and the oxides, yep, maybe they can become something that can be valuable and end up going to a customer. So that would be the ideal. If you could do that, and you could get all that out, not ruining anything to the environment, and anything you make, you sell to a customer, and the customer will pay you money for it, and that'll pay for the process. Well, the next slide, we've got the Dross processing economics. We all know we live in the real world. So, okay, you've got casting plants, you've got the process plant. Let's say it costs $100 million a year to run a fancy, advanced Dross processing plant. 100 million a year. And the people who put the money into that thing, they're going to want a profit. They're going to want, let's say, $20 million a year back to pay for the profit, to pay for the investors, to pay for the equipment. So you've got 120 million bucks a year to run that plant. Only theoretical numbers, 100's a nice round number. Doesn't matter what it is. They've got customers over there and we want to sell them stuff. Well, let's say what you can sell to them is only 60 million. Okay, so all right, that's 60 million of your half of your 120. You've got covered half your costs. You know what's coming next, don't you? How are they gonna make that happen? We all know they're going to charge you a fee. You're going to have to pay a fee to process your dross. They're not going to give you money. So the other 60 million is going to come out of the people getting rid of the dross. I don't know what the number is, who knows? But I think we can all see that down the track, we might have to allow $1, $2 a kilogram, $3 a kilogram for dross. You might have to say, that's what it's going to cost us. We have to build it into our business, and that's part of the cost of making castings. We don't know, but I think we can all see that's coming. That's it.
Just out of it.
Yeah.
I better stand in front of Gary's camera. Here we are. When we say this is the end, it's really not. It's really the beginning. Because effectively ADCA wants to take this a bit further. We would like to have a meeting with the EPA and explain the importance of our industry in the terms of all the way down to sand casting, and we'd like to join with the AFI to say, as a group, we go along to them and say, look, the way we're progressing with legislation, you could put us out of business in 10 years' time. That's the way we're heading. So we've got to try and do something first. So we're going to get together and ask the AFI to join us, because strength is really within all of us going together as an association. Going individually is very difficult, right? Sure, you'll make a noise, but you won't go far. So we would like to take everybody and go along as ADCA and AFI and tell the EPA that we have a problem, and part of the problem is you. And we want you to understand our problem so that we can solve this together. Because I'm sure around the world, the same thing is happening in every country. They have most of our laws come from Europe. That's where they kind of originate from. And those laws are the ones that are driving our headaches. And so we need to be able to, as a group, go along and make some noise. So that's our next plan. Thank you.
I think there's probably going to be questions, so